we're going to introduce a new construct called a matrix. So a matrix is just an array of numbers. I say to you a matrix has m rows and n columns. Remember, we've seen this notation before. You can think of a matrix in terms of individual entries. If the matrix is capital A, its individual entries will have lowercase a. The first subscript refers to the row. The second subscript refers to the column. The first row of the matrix will go from A11 through to A1n. If we keep going on with this convention, I'm hoping you can see the pattern. This is the most general way to write a matrix, but it's not the useful way at all. This is like a raw data dump. When somebody gives you a matrix, they will give it to you in entry form, but it's limited in its use. We are going to make use of two other forms that are much better for us. We are going to talk about something called the column form. Column form of a matrix is more conceptual. I'm going to take each one of the columns and write it in terms of vector notation. We are going to write the matrix as a box that holds columns. The notation is going to be lowercase a with the vector symbol. So that will refer to column 1. A2 will refer to column 2, and this will go all the way down to AN. This is more for conceptual understanding. It's by far the most important version we're going to have of a matrix. Now there's another form that we are going to use as well. We're going to use row form. Row form is mainly for calculations, but it will simplify a lot of what we do. Instead of talking about the columns, we are going to take the top rows here. That top row up there, I'm going to put a capital A1 with the vector symbol, and I'm going to put these horizontal lines to really emphasize to you it is a row vector. It's a sideways vector. Because this matrix is m by n, the very last row will be a subscript m. Each one of these AIs is a vector that has n entries, because remember, it has to go across all of the columns, whereas in the column form, each one of the little AIs is a vector with m entries, because it has to encompass all of the rows of the matrix. As an example, here is a matrix. This matrix is 2 by 3, so it has 2 rows and 3 columns. This would be A1, A2, A3. Each AI lives in R2 because they only have 2 entries. Whereas if I were to talk about the rows, this would be row vector A1, this would be row vector A2, and each one of these AIs has to live in R3 because it's a vector with 3 entries. There are a lot of special matrices that we are going to encounter throughout the semester. We are going to have something called the zero matrix. The zero matrix is just a matrix filled with zeros. You just tell me the size of the matrix. Far more useful is what's called the identity matrix. The identity matrix is essentially the matrix version of the number 1. We're going to use this notation, I, and it's going to be an n by n matrix. The identity matrix is the matrix that has 1s along the diagonal and then zeros everywhere else. So I'm putting these giant zeros to encompass all of the little individual ones because I'm lazy and I don't want to write them out. If I give you a system of linear equations in standard form, we've already talked about the way to put it into this augmented matrix form. We could think of this first column as a vector, and I'm going to call it A1, and this other one as A2. Our right-hand side is going to be called B. So we could write this in a shorthand symbolic form, A1, A2 augmented with B. We are going to go ahead and introduce some new notation or a new way of writing things. So we're going to make a definition called a matrix vector product. I'm going to call this the conceptual definition because everything we do in order to come up with new ideas, new concepts is going to rely on this version. It uses the column form of a matrix. So we are going to let our matrix be m by n, and we're going to write it in terms of these columns, A1, A2, all the way down to AN. Each one of these lives in Rm, and we're going to let our vector x be a box that holds scalars, some numbers. The number of entries in X matches the number of columns in the matrix A. So if we have that, then we are going to define the following. We're going to come up with this new notation AX. This is a matrix vector product. The matrix A is multiplying this vector X. We are going to write it as the matrix, the box holding the columns. And we're going to write it side by side with this box holding these numbers. And it's going to be the linear combination form that we talked about last time. So the first entry of X is weighting the first column of A. The second entry of X is weighting the second column of the matrix A, and so on and so forth. So Xn, An. And this is why the number of entries in X has to match the number of columns in A. We can write our linear system in a much more compact form. AX equals B. And this is the notation we use throughout the whole semester. Every linear system we deal with is going to look like this. Just as an example, a computational example, this is the system we had earlier, 8, 5, 1, -1, 4, and 3. And our vector, let's just pick a vector. Let's say it's 1 and -1. Now remember this matrix here, if we use this definition, we think of this as A1 and A2. Each one of these AIs lives in R3, 3 entries. There are 2 columns, so that means this vector has to have 2 entries. If I go ahead and I write AX, that means I'm taking the first entry of X and weighting the first column of A and adding it to the second column of A weighted by the second entry. So the first entry of X is a 1, and that's going to weight this column 8, 5, 1. The second entry of X is -1, and it's going to weight this column. Oh, sorry, I forgot a negative here. 1, 4, -3. That means I'm going to get 8, 5, 1 plus 1, -4, 3. And if I add them together, I'll get 9, 1, and 4. So what this essentially does is it gives us many forms for a linear system. You could write a linear system in standard form. You could write a linear system in linear combination or vector form, which you have x1, a1, x2, a2, all the way down to xn, an equals b. You could write it in augmented matrix form, which is just basically A1 is the first column, A2 is the second column, all the way down to AN, and then there's a right-hand side. But now we've got this new matrix version, AX equals B, where A is a matrix that has all of these columns, and X is a vector that holds all of those individual entries. Remember, the number of entries in X has to match the number of columns in A. There's something in the book, a result that is common sense, but we just need to be thorough. The solution set to all of the above forms are equivalent. You're going to get the same answer to all of those systems, regardless of which one you choose to solve your system. It doesn't matter which one you use, they'll all give you the same. Now, here is a very important property. This is something called the linearity properties of matrix vector products. In calculus, you learn about the derivative and you learn about the linearity rules, and those ideas come up again here. And so what do I mean by that? If you ever decide that you need to take a matrix times a scalar multiple of a vector, by this theoretical definition, this is going to give you the following. You're going to have your matrix A1 all the way down to AN. CX is a vector that has CX1, CX2, all the way down to CXN. So by definition, this is going to give me CX1 times the first vector, and that's going to continue down to all of them, CXN times that last vector. All those C's and all those X's, they're just numbers. So there's a common factor of C that I can take out of every single one of those entries, and what I'm left with, by definition, is just C multiplied with that product AX. And so just like in calculus, the derivative of a multiple is the multiple of a derivative. The matrix vector product of a multiple is the multiple of the matrix vector product. Now another version here, if you wanted to take a matrix times the sum of two vectors, your matrix is best thought of in terms of columns. Now, by definition, the sum of two vectors is just a column that holds all the individual sums. By definition of a matrix vector product, this can be written in the following form, and then you can split it up. You just have basic properties of addition, and as you go through and you write this all out, it's very straightforward to see. This breaks down as you would expect it. So we get something very similar to like you saw in calculus. The derivative of a sum is the sum of derivatives. This first entry is AU, this second one is AV. The matrix vector product of a sum is the sum of matrix vector products. Those properties are pretty straightforward and you get to use them throughout, so I'm not going to fuss too much about them. There is one last thing that I want to mention, and it's a different way of writing a matrix vector product. So this is what I'm going to call the computational form of a matrix vector product. Now, this is relying on a new idea that isn't written in your book yet. So I'm going to define something called a dot product. We're going to talk about the dot product of two vectors. They both live in Rn. That means they have entries u1 down to un, and v goes from v1 down to vn. I'm going to write this notation, u dotted with v. The definition of this dot product means take the first entry in u and multiply it by the first entry in v, then go u2, v2, all the way down to un, vn. As a very basic example, if I say u is 1, 2, and v is 3, 4, then the dot product of u and v is going to be 1 times 3 plus 2 times 4, which gives me 11. And so note, the dot product is always a number. Why do we care about this dot product? The dot product gives me another way to compute AX. Now, I'm just going to give you a 2x2 example here. If I have a matrix, let's say I just have a 2x2, you could think of the matrix in terms of either 2 columns or 2 rows. According to the definition of a matrix vector product, I would have 2 columns like this, multiplied by x1 and x2. If these 2 columns kind of look like this, alpha, beta, delta, and gamma, x1 and x2. The definition says I'm going to have x1 weighting this first column, alpha, beta, x2 weighting the second column, delta, gamma. If I use vector properties, this could be alpha times x1 plus delta times x2, beta times x1 plus gamma times x2. This final answer that I get could have been obtained in a different way. This top row is a delta, and this vector here is x1, x2. So this top row of my answer is actually the first row of the matrix dot product with x, because this whole thing is x. The second row of the matrix then also takes a dot product with this to get me the next entry. So this would be a2 dotted with x. I defined something called the computational form of a matrix vector product. So a matrix vector product in computational form, if I were to take a matrix and write it as a collection of rows, remember the matrix is still m by n, and I have a vector x, the vector x has to live in Rn because the number of columns needs to match. I could get my final answer as a1 dotted with x all the way down to am dotted with x. That gives me, in some situations, a more straightforward way of doing it. How does it work? Very simple. You take the top row and you have to multiply it by this with a dot product. So it'll be 8 times 1 plus 3 times 2 minus 4 times 3. And then you take the next row, turn it sideways, turn it into a dot product and multiply with that. So you'll get 5 times 1, 1 times 2, 2 times 3. Your final answer has to have 2 entries because remember, a matrix vector product says first column, first weight, second column, second weight, and then you're adding a bunch of vectors that has 2 entries. This is an alternate form of doing it, but it has to give you the same result. So upstairs, you're going to have 2, 5 plus 2 is 7, plus 6 gives you 13. And you should check that. You'll get the same result when you do it the other way.